point that we had for over 2 years, and we ran the classification across the group. So we got a good accuracy, about 81%. But we wanted actually to see if we can predict early than 2 years. So we use 1 year data based on the class labels that we had. And we got about 75% accuracy. So in that way, this is actually to predict which participant is likely to be remitted or converted or maintained after 24 months, when the model was only trained by the data at 1 year. So that was the maximum accuracy that we could get when we use 1 year data set into 3 classes that we had. And lastly, I would like to acknowledge all the team that without this expertise and these great people, these projects was not possible to be conducted actually. And from AUT, University of Auckland, University of Waikato, and many, many more, so you can see here. And this is just an acknowledgement, so of course. Lastly, I'd like to mention all the things that I just mentioned about our research. Still is going, and we are developing mainly the research area that we are working is in neuroinformatics, bioinformatics, and also for any case studies that we are working mental health is understanding multimodalities of the data and integration of them in one unifying model using like a longitudinal data for the purpose of prediction and classification, and using and developing advanced AI tools, and also for the individualized modeling. If it's in the case of treatment, it's more personalized therapeutics and identification of biomarkers, of course. So these are the areas that we are working from our team in New Zealand at the University of Auckland and Auckland University of Technology. And please keep in touch with me if you have any questions around any aspect of that what I just described, or if you're keen to collaborate. And I am very happy to discuss every aspect of our research. And please keep in touch.
Surgical department, and with that, the biopsy tissue, they can perform a bunch of techniques like hematoxylin and eosin stains that you see on the top figure. Immunostainings, you can see an example of that in the bottom figure, and various gene and proteomic assays try to reach a conclusion in the prognostic and diagnostic outcome. And H&E stainings tend to be used to look at nuclear states, nuclear cell shapes, and also give a very good overview on the tumor microenvironments in that tissue. And to help the pathologists hone in on their conclusion about the prognostic and diagnostic outcome of the patients, they use techniques such as immunofluorescence and further gene and proteomic assays to kind of find markers and diagnostic, basically stain for biomarkers that have prognostic and diagnostic values. These can be cell-specific, and it can also be associated with human microenvironments. Hematoxylin H&E stains are relatively inexpensive, and they're pretty fast and standardized compared to other processes. And while the immunofluorescence or immunostains and other assays can provide a much better resolution in terms of what kind of markers there, but they can be very expensive, and a pathologist would require multiple rounds of these sort of stainings and assays to reach their conclusion, because unfortunately the initial rounds will always have to be a stab in the dark in terms of figuring out what sort of markers would be present in that tissue. Now, emerging research in the GBM space have started to utilize AI and machine learning techniques more often than in their research, whether it be aiding them in tumor segmentation or classification of various tumor types, to maybe even prediction of certain patient outcomes. And general trend that we see in that GBM research space right now is that although a lot of the research do acknowledge GBM's heterogeneous nature, they tend to focus their research on specific aspects of GBM, which we believe they do not kind of encapsulate the heterogeneity of GBM. And despite all this research leading to a big evolution on how we can diagnose and grade GBM tumors in the recent years, the regimen for GBM remains largely unchanged, and patient outcome has not really improved. With all this in mind, we ask ourselves, what if we could overlay the H&E patterns that we see, H&E features that we see, with a large panel of biomarkers that we can get from our immunofluorescence staining, our immunostainings, and sort of put them together to contextualize these vast panel of biomarkers that could that could relate to different aspects of GBM, and contextualize these biomarkers to the H&E features, and B, also fingerprint our H&E data. And that way we can build a model that could kind of predict these sort of biomarker mappings based on the H&E stains. This would likely reduce the amount of guesswork that the pathologists would need, as they can just use this to predict what sort of markers that they should be looking for first. And it would really streamline their processes when they try to diagnose and prognose. And together with this fingerprinted data, we can combine it with patient clinical records to create a model that can predict various patient outcomes and aid in the pathologist in reaching the conclusion of diagnosing and prognosing the patients. And the culmination of this multi-scale approach to our fingerprint data can ultimately better stratify and accurately represent GBM heterogeneity, which can serve as basis for personalized treatment of GBM.
Maybe try using that.
No, I am for Project A.
Yeah, because I use a lot of transformers.
Is to develop a multi-scale platform that can spatially resolve larger patterns as well, generative adversarial networks to kind of supersede our current method of random oversampling of our minority classes, because I think that by synthesizing that, it will be a lot better than just oversampling from what we have. It will just be too much overfitting if we just oversample like that. Yeah, and that will be applied onto the second iteration of our model.
Did you present this in here? No.
They said no.
Okay. Okay, thank you, Jeff. Can you minimize the distance?
Yeah.
In the big computer, not your computer, the other computer. You can minimize the distance of the attendees. Otherwise, sometimes the hidden side.
Would that be better?
Just
yeah. And I'll just stop screen sharing.
I'll go use my own laptop.
Then.
Yeah.
So you leave your laptop over there, or you there?
Yeah, I can leave my laptop there.
Okay, that's convenient, I think.
We can use the field.
Oh, yeah, for sure. Sorry, I had a blank.
That's got a USB. It's
Yeah.
plug in. Thank you. So far. Okay, but if you're,
Do we screen through that? That's
that's very close. Okay. Oh, correct.
Not sure. It's muted on my end.
Oh, maybe it's okay. It's better. Hi. I'm doing stroke lesion segmentation for the MRI. And I'm a master's student here at UA, and yeah, I'm Zion. So I just want to introduce my public data set I've been using now. It's called the LS 2.0. So it's the very recent data set provided by the Brain Challenge thing. So it's released in 2022. I've been using that data, and it contains a lot of data set, which is 655 T1 training images, including the ground truth, and it has hidden test data provided by Ben, what I can check there right now. It's also good because it's registered to the MNI in the 52 space, and it's been normalized with the MIS token. So for the pre-processing for my side, I just did the Z-score normalization, which is like a common method used for any of the brain images. And I've also ran the N4 bias correction method using the ANS token. It's for correcting the low frequency and increasing the intensity, the uniformity, for it to increase the contrast and recognize them. So the mean intensity increased from 77.8 132.0. And I've also done the score stripping provided by the FSL software. It's using HD2. And by using that, I've achieved a higher dice score of points that went up by 0.03, which is pretty big. And I also used another 5-cross validation there. This is an image of the framework that scored the first place in the Grand Challenge. It used a 5-ball there. See the image there on the right bottom. That's the lesion size. So by buying those lesion sizes and by evenly spreading out by 5 balls, we can achieve a much better evenly spread out data set. And after assembling, then you just get a better output of the dice balls. And I just want to introduce like common models there. That's really brief. Right now, these days, stroke lesions only use the UNets right now. And they use encoders, decoders, and skip connections between the two to retrieve the better context informations. And another one would be attention units, where we use the attention gates to have those selectively have those lesion sizes and increase the weights on those ones. And nowadays, past few, I think it's 3 years, we're using transformers there. And it's the one that I'm using a lot, so it can effectively retrieve the global context information there. Because Atlas has a lot of different lesion sizes, which are very small and really big, and it's seen as a state-of-the-art method right now. So the models I've been using are based on those PyTorch Lightning unit framework. I've always used 1000 talks. I've used Adam Optimizer and Adam W, and I'm not thinking back to difference.